Hi, I'm Adil El-Mumni, Rheology Product Manager at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging windows to your liking. You can resize the video and slice windows independently from one another by clicking and dragging the bottom right corner of each window. If you get disconnected at any time, please use the instructions you have received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. If you need any help, click the question mark widget. Please ask any questions you may have at any time during this presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. I have the honor to present our guest speaker today, Professor Chris Macosko. Chris Macosko is Professor of Chemical Engineering and Material Science at the University of Minnesota. He has advised nearly 100 master's and doctorate students, with whom he has published over 400 papers in rheology and polymer processing, particularly processing with reactions such as reaction injection molding, polyurethane foam, cross-linking, and compatibilization of polymer blends. This research has been recognized with numerous awards, including the Bingham Medal of the Society of Rheology and election to the National Academy of Engineers. We're very happy to have Professor Chris Macosko speaking with us today. The title of his talk is Analyzing Polymer Molecular Weight Distribution and Blend Morphology Using Rheology. Chris?
Thank you, Adil. I'm excited to be here and to tell you about how we can use rheology to look at molecular weight distribution and polymer blends. Polymer blends can be divided into miscible ones and immiscible. The miscible category can further be divided into homogeneous and heterogeneous. Homogeneous means just basically putting the same polymer together, different molecular weights, and that's why I mentioned we can get to molecular weight distribution by analyzing those kind of blends. Immiscible blends is the large category. Practically all plastics that we get today are some kind of a blend. So I think this is a pretty important area to try to understand, and rheology is a powerful tool to analyze them. Let's look at some applications, examples rather, of miscible blends. The simplest is, as I said, a high molecular weight and a low molecular weight to lower the viscosity. I show an example with polycarbonate. But there are also a few cases of heterogeneous, two different kinds of polymers being blended together. Here's several examples. For example, polymethyl methacrylate can be blended with polyvinylidene fluoride, which has excellent chemical resistance, but the clarity of polymethyl methacrylate can give a good optical properties. So that's one reason that's a popular blend. So let's first look at the homogeneous blends. I think you probably know that polymer viscosity changes very significantly with molecular weight when you go above the entanglement molecular weight. So we have here a log-log plot of viscosity versus molecular weight, and you can see a break there. The blue curve is a slope of 1, and then it jumps to more than 3 times. We can think about entanglements a little bit like spaghetti. You know, when you grab with a fork a bowl of spaghetti, you might pick up nearly the whole bowl because the noodles are entangled with each other. But if you go shorter and shorter with your spaghetti, you eventually get to macaroni, and the resistance is quite a bit less, and you can't get the whole bowl up. So I hope that helps us to understand a little bit what we're up against and why rheology is so powerful in characterizing. We can really be very sensitive to the high molecular weight. Pierre Degens came up with a model for this called reptation, which means moving like snakes. So in French, it's invented a word really. And the chain, we can think about the chains around the central blue chain as the entanglements, and they form a channel or a tube that restricts the motion and takes a lot longer and therefore raises the viscosity. And one parameter that's important is the molecular weight between entanglements, and I tried to show that there with the red line on the graph. We can put this together, well, we can see an example of this experimentally. So that's a theoretical idea. Degen's got the Nobel Prize in physics in 1991 for this and some other theoretical understanding of materials. Stephen Chu at Stanford got the Nobel Prize in 1997 in physics for these kinds of experiments. And so what we see here in this slide is this red dot is a polystyrene bead that Chu and his coworkers could move with a laser. So it's they're called optical tweezers. So you can actually move little things around in a liquid with these optical tweezers. And on the end of the polystyrene bead is a DNA molecule that's been fluorescently labeled. And what they did was actually make the letter R by moving the DNA in a liquid. Now the blue background is also DNA, but it's just not fluorescent. So it's a highly entangled liquid, and it looks a lot like the spaghetti that we see here. But you just can't see it. And now they formed the R and then just waited with time. So this is a time-lapse photography. And you can see that what's happening is the DNA is moving along its path. Can you see that? Moving along its path with time. And this took over a minute for this to happen. This is the idea of reptation, moving along the channel. So I'm going backwards, sorry, learning this key. Apologies. Okay, there we go. We can translate this. Rheology is very sensitive to pick up that time. Here we see the elastic modulus as a function of the frequency of oscillation. So you can think of frequency increasing to the right there would be like the time decreasing. So shorter and shorter times to the right, longer times to the left. And we've got 4 different molecular weight polybutadienes shown here, and they're expressed in terms of the entanglement molecular weight. The red curve is about 9 entanglement molecular weights, and the dark blue one is in a much higher molecular weight. And so we can see that that time is longer and longer. At 1 reciprocal second, that would be a 1 second, and we move into milliseconds as we go to the right. And you can see that labeled. The longest relaxation time here on the red curve, which is 10 entanglements of polybutadiene, is about 1/10 of a millisecond. But rheometers can make those kind of measurements. The other thing you notice in the graph is a flat line. So that means that for a certain period of time, the polymer acts like a cross-linked network. The entanglements act like cross-links, but they're temporary and they eventually relax. So we call that the longest relaxation time, 1 over the frequency in this plot, and then the plateau modulus, GN0. And these are the 2 key parameters that allow us to estimate the molecular weight from rheological data. This other curve just shows you the loss modulus. So we have the elastic modulus and the loss modulus, and we see that that goes through a maximum. Here is the model for reptation. So again, we have a little, up in the right-hand corner of the slide, we've got a little cartoon showing the entanglements creating a tube. And the longest relaxation time you can see is a function of the molecular weight. The molecular weight to the 2nd power, and then the 1.4 power, you add those 2 together and you get the 3.4 power. Molecular weight divided by entanglement molecular weight. The other parameter in this longest relaxation time is this segmental friction, that Greek symbol psi shown there. It looks a little wiggly symbol. And that's the friction in the tube. And that depends on the glass transition temperature, how far we are. You see T minus T sub G, how far we are from the glass transition temperature. The higher the temperature, the less the friction, and that will be subtracting, you can see there, from the glassy friction. So those two parameters then control the relaxation time, and then the plateau modulus is the level that we're at. Put those together and then you have the viscosity. Now, that's for a single reptation, but let's see how that looks, how that can fit some data. So we have the, let's go back one, and whoops, we see the G double prime plot as a function of frequency there on a log scale, but if we put it on a linear scale, that maximum gets highlighted quite a bit more. So let's move forward and see that maximum. Then you can see it looks like a peak. And we can fit that quite well, especially on the left side of the curve. There shows a 71,000 and a 355,000 molecular weight polybutadiene. And now if we blend those two together, we don't get a very good fit. Can you see the solid curves are the fit and the dotted lines are the data? We're really over predicting the low frequency or the low molecular, the high frequency rather, or the low molecular weight material. So what, if we go back, what Tsunoglu did was say, use the square root and then add up the relaxation times, and that really works quite well. It's kind of a simple rule, and that's been put into software, and you can see that when you use the double reptation, you get a much better fit in the lower right-hand curve, you can see from the slide there. Here's just an example of how sensitive rheology is. We blended a 4 million molecular weight with a 400,000. We only put in 1%. And if you look at the molecular weights plotted there, you can see a very small change, that 1%. We've blown it up and with a little red arrow. But in G, if we look at the change in G prime, especially at low frequency, we get 4 times the change in G prime. This shows software that can be used to take the G prime and G double prime data and calculate the molecular weight distribution. So on the right side is the rheology data, on the left is gel permeation chromatography, or also called size exclusion chromatography. So here's a narrow molecular weight, 400,000 molecular polystyrene, and now we add in 1% of a 12 million molecular weight. Notice you can't even see the change on the GPC, but already you see this nice bump in the G prime at low frequency. And if we go to 2%, it's very pronounced. Now, this is a quite high molecular weight, so it has a huge effect on the G prime data. You still can't see it in the GPC. At 4%, we can barely detect it. So rheology, especially for when high molecular weight is added to a material, or if there's a high molecular weight tail from your reactor, rheology is an excellent tool. And the rheology can be analyzed to predict the molecular weight distribution. Here's a practical problem, extruding high density polyethylene for tubing or for pipe. And you can see the viscosity on the upper curve between these two samples, your two commercial samples. The viscosities are very close, very hard to distinguish between them, maybe a little bit at the lowest frequency. But the G prime, the elastic modulus, shows that the blue curve has a much higher molecular weight tail on it, and that caused surface defects during extrusion. It was an excellent correlation between extrusion problems and the rheology. Well, this is the homogeneous blends, as I've mentioned, and I think we have a good handle on that, and we have a good simple theory, and it's available in the Rheometer software. Let's look at heterogeneous blends. As we mentioned, there are several important examples, and how can we model them? They're still entangled, as shown in the next slide, but now we have red chains entangled by blue chains. We can still use the double reptation, but the thing that is different is that the friction of one chain is not the same as the other. So we have to bring in an understanding of the difference in friction. And so I put the strategy of the calculation is to estimate the longest relaxation time. And now in red, I've indicated that a study by Lodge and McLeish allows us to estimate this segmental friction, and then we can go on further and calculate the viscosity. So the source of the problem is really that you can't just use the average. You might say, well, I'll just take, if I have a 50-50 blend, I'll use the viscosity of one and divide it by half, and then the viscosity of the other polymer, and then add them together. You can't use a simple mixing rule because, as said on this slide, the monomer, that red monomer, I said A there, that type of monomer, has more of itself around it because it's connected. So it's, as we say there, due to chain connectivity alone, the segment of type A experiences more of its buddies next to it. So you imagine there are 9 nearest neighbors, or 8 nearest neighbors there, and 5 of them are red and only 3 of them are blue. And so that's a problem. Kind of call it self-concentration. We look here, for example, you can see the structure of the polyisoprene, and then also the structure of polyvinyl ethylene shown there. And you can imagine that the polyisoprene monomer unit is bigger, and so its self-concentration is 0.45, and the polyvinyl ethylene is 0.25. So there's a difference in self-concentration, and that needs to be considered in calculating the friction. So if we, so this phi S sub S is a self-concentration. We can get that self-concentration from differential scanning calorimetry. So this shows a DSC plot of the heat capacity as a function of temperature. So we heated up the polyisoprene, 100%, that's the black curve on the top. We heated up the polyvinyl ethylene on the bottom. And they have a sharp glass transition temperature, about -60 for the polyisoprene and about 0 for the polyvinyl ethylene. These are rubbery materials, and we're blending them together. But notice at 50-50 particularly, what's the glass transition temperature look like? What do you see there? It's very broad because we're really seeing the friction of both kinds of chains. It spreads out that glass transition temperature. And so that's what this theory takes into account. So we can fit the average value by something called the Fox equation, fit the average TG value, and then we estimate the effective TG. So let's see, go forward, yes. The effective glass transition temperature of around each monomer unit. And so you can see the average is the green curve in the middle, and then the 2 dotted lines are the effective values. So if we go at 50-50 and walk up to the lower curve, that's the effective glass transition temperature of the polyisoprene, and its effective concentration is about 70% instead of 50%, and then the polyvinyl ethylene is about 30%. So they're really different effective concentrations. So you bring that in and you multiply that to get an effective glass transition temperature. And we bring that into the friction. See the second equation on this slide is essentially exactly the same equation I have for the homogeneous blends, but now I just changed the glass transition temperature. And it's kind of cool. We didn't need we just had to get some DSC data, and then we can use the rheology that we had, and then we put that friction, so I've marked in red the Xi term there that we've changed now with the glass transition temperature. And then we can use the same theory. We also have to change the entanglement molecular weight as just a mixing rule average because the entanglement molecular weights of different chains are different. Put that back together and you can predict. So here's again the strategy. Again, use the same Tsunoglu mixing rule. So it's the same equations really, but just with a different friction factor. And here now is a blend of 78,000 polyisoprene and 120,000 molecular weight polyvinyl ethylene. And that would, if you just ran a straight line through the data at 0 and 100% polyvinyl ethylene, it wouldn't be bad. Just a mixing rule would work pretty well. But now, just change the polyvinyl ethylene molecular weight and see what happens. Notice it's no way linear, right? Depending on the temperature, it's all over the place. And this model can do a very good job of, it's not a perfect fit, but it's a very nice job of predicting. So if you, for example, the lower green curve, if you pass a straight line, you'd be pretty far off. But with DSC data, you can do a good job of fitting it. And that's just a summary of 4 different miscible blends and showing all kind of different nonlinear behavior, either positive and negative deviation from a simple mixing rule. So this summarizes the second part of our miscible blends, and maybe, well, actually all of them, but in the homogeneous case, if we know the density of the material, and we have the friction term and the plateau modulus, we can do a good job of estimating the molecular weight distribution from simple G' and G" data. You can take that data in half an hour after you've loaded your sample and get a real good idea, especially of any presence of high molecular weight. And then we showed how to modify that approach to get for heterogeneous blends, and we need to add DSC data to what we would have above, and we would be able to do a good job of modeling that. But let's move on to immiscible blends. And I want to emphasize that this is a very large category of materials, and we can also use rheology to understand now it's a heterogeneous system. We have 2 polymers there, phase separated, and they can have lots of different morphologies. The most common one is shown up in the left corner of the slide is the droplet blends. But you can, I'll also say a little bit about cocontinuous blends in the talk, but I'll focus mainly on droplet blends. And I think a thing to remember is a nice quote from Richard Stein at the University of Massachusetts, that morphology without understanding the rheology is like zoology. It's just kind of a categorization of things without an understanding. So I think the rheology can help us a lot. Droplet blends are made for a lot of different applications. I tried to show you in that image that there's a little bit of the droplet on the surface, and that's one application. It's shown on the next slide, surface modification. So for example, Dyneon, a division of 3M, puts in a little bit of fluoropolymer into, say, polyethylene. 1% of that will get to the surface and make it a lot easier to process. It'll allow people to process it at a higher flow rate and increase productivity. So that's one example. Another big area is for toughness. Super tough nylon is an example from DuPont. Let's look at a couple of morphology images here. Here is the super tough nylon. We can see that rubber particle diameter makes a big difference in toughness. So we've plotted here impact strength versus particle diameter. And you can see that we don't gain any toughness until we get the size down below, depending on the concentration. Here I've shown 20% of rubber in nylon, and when we get the size down below about a micron, you get an order of magnitude increase in toughness. So this was a great invention by DuPont and really improved nylon. So we're going to see how can rheology help us to see the size of these particles. Another example are layered structures, barrier blends. And if we can get a sheet-like structure in, then we can have a much better barrier. So the lower curve is droplets and the upper curve is lamellar, and that shows that we've, even with 5% of layered structures, you can cut the diffusion by a factor of 10. Here's how the morphology develops during processing. So we've tried to show a little polymer pellet on the left side of the slide, and as it melts and gets sheared, it gets stretched out into sheets, and if you can trap those, you'll have the barrier blends. But usually there's lots of mixing going on, and the typical final state is some kind of droplets. And one goal is to compatibilize and get the droplets small enough, as we saw in the nylon blends. We'd like to get those droplets below a micron to be effective for toughening of the material. Now, rheology tells us something about the size of the droplet because the drop increases the viscosity. We know that for dilute concentration of spheres, rigid spheres, is the simplest model. In fact, Einstein came up with that when he was trying to understand Brownian motion in 1905. And so the term in parentheses there is what he developed for very dilute, sort of 1% droplets. They increase the viscosity 2.5 times the concentration, which is interesting in what it's doing. The particle disturbs the flow streamlines, as I've tried to show there in the cartoon. As you go to higher concentration, then it depends on the volume fraction squared. Batchelor developed that term. But if you go much higher than about 5 to 10%, you really need a different equation, and Krieger and Doherty came up with the equation down below, which brings in the maximum concentration that you can pack into the system. So if you know the maximum concentration, then you have a very good fit, those solid lines there in the lower graph. So starting from that basis allows us to understand the drop size. Let me show you how that works. The difference, though, with blends is the drops are deformable. And so you can show here the dotted line was a sphere, and now we start shearing it, and what happens? The drop gets stretched out a little bit. What is causing it to come back is the interfacial tension, and I show that as a capital gamma in this slide, and I show the radius as A. So this, if I stop the motion, for example, I'm shearing it, I stop the motion, the drop is going to come back to the spherical shape, and that comes back more slowly if the viscosity is high. So the relaxation time of that droplet depends on the viscosity. The restoring force is the interfacial tension, which is bringing it back. So the relaxation time, we now have a new relaxation time. Remember in the beginning of the talk, what was the relaxation time from? That was from the reptation of the chains, sliding through the friction of the other chains that were entangling it. Here, the droplet is relaxing back due to the interfacial tension. That's driving it back. The higher the interfacial tension, that big gamma, then the lower the viscosity. And then that can change the G prime. That adds an extra relaxation. Just like the high molecular weight added an extra relaxation, the drop adds a relaxation. Let's look at some data and get an idea of what this, how this actually plays out. So here is now, just like when I added a little bit of high molecular weight to a polystyrene sample, high molecular weight polystyrene. Here I take polystyrene. I'm going to add a little bit of polymethyl methacrylate. And at 2% of PMMA, we don't see too much change. There is a little bit of change you could see in the G prime, but if I go to 5%, you can start to see a bump in the G double prime, G prime rather. You see that red arrow. And then as we go to 10% and 20%, it's very obvious that bump. And that little bump is an extra relaxation time. The first drop in G prime, of course, is from the reptation. So we really have two kinds of relaxation. The chains are relaxing, and that's at frequencies, let's say, of about 10 radians per second. So that's like 100 milliseconds is the relaxation time. And these drops are relaxing at 0.03 relaxation. So that would be like 30 seconds. They're taking a long time to come back because of the high viscosity of the polystyrene around them. So they're pretty separated as a nice example. And to prove the point, we have some transmission electron micrographs that I can add. There are some small droplets at 2%, and here at 5%. You can see them at 10% and 20%. 20% now you can see the drops are many different sizes, so it's a little bit broader shoulder there. But all this can be analyzed by the model of Palierna by putting in the drops with their relaxation time. The interfacial tension would be constant for this pair, and so you can get the radius of these droplets out. And so again, by analyzing the shape of those curves, we can actually get a drop size distribution. And we see that here in this plot. We've plotted a frequency V, that's a concentration of drops, against the log of R. Here I used R for the radius rather than A. And you can see B02 is 2%, and the drops are about 100 nanometers, 10 to the minus 7 meters. And then at 5%, it's up at about a little bit, maybe 200 nanometer in diameter. And then as we go to 10%, the drops get bigger. Why? At the higher concentration, there's more collisions, and so the drop size gets bigger. And you can see the dotted line is the calculations by rheology, and the solid lines are analyzing the electron micrographs. And really excellent agreement at 2 and 5%, not too bad at 10, and at 20 it's bimodal, and we can't really do a perfect job, but you're certainly seeing the effect there. Now, what about, that was sinusoidal oscillations. What about steadily shearing them? Again, I show you the relaxation time, lambda there. Now, we have something like the Einstein equation, but we have, you can see the volume fraction, phi, and then we have a term in front of it. You can see the 2.5, 5 over 2, but it's now times the viscosity ratio, and that's the viscosity of the liquid inside the drop divided the liquid on the outside. And so that makes the effect on the viscosity a little bit smaller. But basically it's the same thing as like the rigid drops. And then the other thing that happens is that the drop pulls back and it generates normal stresses. So if we have a shear flow and then we'll have some pulling back, that will push the streamlines apart, and that gives you a normal stress. And we can measure that in rheometers. For example, in the cone and plate, we can measure the normal force. So we can measure the viscosity increase due to the droplets present and the normal force, and that's shown on the next slide. So here is a different blend, polydimethylsiloxane, a silicone melt at room temperature, and polyisobutylene, another room temperature melt. So this is at 25 degrees, and we blended those together, and we can see that the at either side where we put a little bit of polyisobutylene in the PDMS, we get droplets, and vice versa on the other side. And the equations I just showed fit the data pretty well up to 15%, maybe 10%, you can see that 20%. And then as you go to many drops, it goes to co-continuous. I tried to show in the middle. But we can predict the viscosity on both sides of it. And we can see also here now I've plotted G prime and the normal stresses. So in the limit, 2 times G prime is equal to the normal stress, and we can see that shown here. What's shown in the middle curve is the G prime of the polyisobutyl of the PDMS, and then the little dotted points you can see, look up from 10, that's the polyisobutylene. So those are the 2 pure materials, and now we put a little bit of polyisobutylene and we generate a big relaxation. You can see that shoulder there, and we also generate normal stresses. You can see they're agreeing at the low frequency, and as we go higher in frequency, they are above the G prime because we're doing a steady shear and we're stretching out the drops. And I've just labeled that curve here, red being the normal stresses, and then the blue being the 2 times G prime. So the G prime doesn't break up and just wiggling back and forth, so you can go up to high frequency or high, but you can't go to high shear rate with the normal stresses because the drops break. And that's shown here. We are doing, we measure the normal stress, and the viscosity goes up and then drops because these big drops break up into little ones, and then goes back up again as we have many drops in the system. And we can see the normal stress increases and then decreases due to the drop breakup, and showed in a cartoon above. So we started with about a 30 micron drop and broke down into 1 micron size. And we can follow this by light scattering as well. The same rheology curves, and this shows at the beginning, the light scattering pattern is nice and symmetric, and as the drops stretch out, you can see the pattern also stretching, and then it breaks up, so it starts to go back to a more circular pattern. There's still some smaller stretched out drops there. So that just, and now I've plotted, in addition to viscosity, I plotted the normal stresses, and you can see that we can also calculate those at either end before we get the breakup, the low shear rate normal stresses. So here's a summary of the droplet blends. As we might expect, simply the viscosity increases as a function of the volume fraction, and it depends on the viscosity ratio. So if the viscosity of your minor phase that you add in is very high, it goes back to the Einstein result at 2.5. This is for low concentration. And at high concentration, we use the Krieger-Doherty equation, where we need to know we should estimate the maximum volume fraction. And then we have a exponential increase as the droplets interact with each other. And the important thing with droplet blends, the first equations would apply to rigid materials, but because the drops can deform, we get an extra relaxation time that depends on the interfacial tension of between the two polymers. So we need to know one more thing to get the drop size. So when I analyzed that polystyrene PMMA blend, I knew that the interfacial tension was about 2 millinewtons per meter, and you put that in, and then you can get out the drop radius A for a sample, and that's a very nice analytical tool. The relaxation time is also manifest in normal stresses, but the problem is if you try to shear a droplet blend, it will break up and into smaller drops. So typically we do sinusoidal oscillations, or we do low shear rate that will not break up the drops, but there's both way manifestations of the interfacial tension. Well, I did show you co-continuous blends, and so I'd like to conclude the lecture by going into that area, which has been less studied as an area we're doing research in at the University of Minnesota. Here's the roadmap of blends, blend morphology, and so we'll go to the case where around 50-50, both phases are continuous. And here's maybe a better image of them. And with a confocal microscope, we can analyze each phase and map them and separate it. So now you can see each phase looks kind of like a sponge, right? And it's some very interesting applications of that, but they're not at equilibrium. They're not, they will start to coarsen. So rheology can help us to understand the phase size and the coarsening. One example is electrically conductive polymers. For charge dissipation, for example, if you have an Apple computer, you need to have charge dissipation. All electronic devices have to have a little bit of charge dissipation, and polymers are poor conductors. So you need to add something to your typical polymer. The trouble with the conducting polymers is they have pretty bad mechanical properties. And so one way is to have the host polymer. We show here in this slide polypropylene or ABS are very tough, and then we have a conductive polymer that can form a continuous path for electrons to not give you a shock in the winter when you touch the screen or mess up your screen. Another interesting example is as a desiccant for pill bottles. You know that you may have opened a pill bottle that's water sensitive, and so they'll have a bag of silica gel in there. And sometimes people eat the silica gel instead of the pill, and so that can be a problem. And this company invented a nice liner inside the pill bottle that is a cocontinuous blend of polyethylene and then a water-absorbable polymer that can absorb the absorb water in the pill bottle. Another example is for battery separators and membranes for gas absorption. And so those are a couple of other examples that we're working on. So how do you make the blend? Here shows an extruder with feeding in the hopper the two polymers and then doing a lot of intense mixing. It's not a thermodynamic equilibrium, so you have to mix it and it'll slowly coarsen afterward. And to make if I go back to make this porous structure, we put in polyethylene oxide, which is a water-soluble polymer. And we can extract that out with water and then leave a porous polymer film that we can use as a battery separator. And we've characterized this with microscopy as well as with a laser confocal microscope. And here is a video that's been constructed out of about 100 Z-scans through our cocontinuous sample. And you can see you're moving through the image. You can see it's been made up of little triangular elements that were taken from the confocal microscope. And you can see the pores that are in our sample. And those pores are going to be valuable as, for example, a battery separator or forming a membrane. Well, how can rheology characterize these kinds of materials? Confocal microscope takes a fair amount of effort to do that. Can we use rheology? Here shows a nice contrast. In the blue curve, we have a droplet blend. It's commercial, it's pretty broad. You see a broad bump due to the droplets of styrene acrylonitrile in polystyrene. And then we have a 50-50 blend in the red points. And by the way, the black triangles are just the pure polystyrene. And you can see that it's not a bump, but it's a tail that goes off on the slide and basically doesn't have a characteristic relaxation time. It's just lots of different relaxation times. One way to plot this is the dynamic viscosity over the elastic viscosity, or a Cole plot. When you have a droplet blend, you'll get a simple, like a hemisphere, a part of a circle, and then another part due to the droplets, and quite different you can see with the cocontinuous blends. You got a very separated second structure. Here just shows some other confocal images. And now the problem, as I said, it's not stable. So over an hour, it coarsens. So each phase flows into itself and makes the pores bigger and bigger. And so we can characterize that also with rheology. And we look at this just shows the analyzing the images, and we can see the pore size changing. Here, unfortunately, we used lambda as a characteristic length. It's not a relaxation time. So please don't get confused, but that's a characteristic length in microns. You can see it starts at nearly 1 micron and coarsens up into the nearly 100 microns. And as we had two different interfacial tensions. So the interfacial tension on the left is very small. By changing the acrylonitrile the ratio of styrene to acrylonitrile, we can make it closer to polystyrene. You have a low interfacial tension. On the right side, the interfacial tension is higher, and so you can see it coarsens much faster. Notice that it's coarsening in 30 minutes in the black curve. And then the other variable is viscosity. As the viscosity is higher, you can imagine that the coarsening is much slower at very high viscosity. And we can see that, so that was the images changing, and now we can see it in the G prime. So that if we pick the G prime in the tail region of that relaxation, we can also see the black curves were the low viscosity, and the G prime of the interface, we've subtracted off the components, and we just have the interfacial material, and we can see that dropping very rapidly. In the blue curve is the viscosity, the high viscosity, and taking longer to coarsen. So a very simple way of seeing the coarsening. If we go back to the images, this is much more involved to take the confocal image, although very beautiful to get it. We get a quick check with the rheology shown here. And we can actually fit the coarsening rate, as shown here, to depend on that ratio of interfacial tension and viscosity. So we change both the interfacial tension and the viscosity, and we have the plot of the coarsening rate for all the different samples. But we can stop the coarsening by having a chemical reaction, and this is called compatibilization. And here's a different system of polyethylene and polyethylene oxide, and we've modified the polyethylene by putting maleic anhydride on it. And that maleic anhydride group can react with the hydroxyl groups on the end of the polyethylene oxide. And this then forms some graft copolymers on the walls of at the interface. This lowers interfacial tension and essentially can stop the coarsening. And if you look on the left, we see without the reactive material, and on the right, with the reactive material, the pore size is much smaller. The other thing that we can see is that because there's polyethylene oxide, remember, we've washed out the polyethylene oxide, so we have a porous structure, just air in there. And but polyethylene doesn't wet very well with water. It's a very hydrophobic. But now we've made it hydrophilic. You can see we put a drop of dyed water there. The drop with the dotted lines on it's been sitting for a longer time. You can see that. We can analyze the surface with X-ray photon spectroscopy, and we can see the oxygen molecules in the red sample, which was with the reactive material. And you can see that image shown there. Just another image of it. And again, the coarsening that we might expect if there's no copolymer. And here we can see the coarsening is stopped. So we started on the left side, the blue material started at about 5 microns and coarsened all the way over 100 in only 30 minutes. But if we have the reactive compatibilization, we started at a lower size, as we saw in the earlier image. We started nearly at 1 micron, and it coarsens to less than 3 microns. We think this just shows the interfacial tension we can calculate with droplets, and we can also show the packing of there's a little bit of area decrease, and so the graft copolymers that were formed by reaction have packed together to really stop the coarsening. And a very stable system then has been generated. And this just shows how the G prime changes with time, and we can see that also in scanning electron microscope images of how the pore size has increased greatly as a function of time for the styrene acrylonitrile system. So to summarize now, we have looking at co-continuous immiscible blends. If we look on the right, we have the characteristic G prime. The squares show the pure polystyrene, and then if we add when we go to the 50-50 blend with styrene acrylonitrile, we see this, we don't get a shoulder. It's just a long, slow relaxation that is no special characteristic time. The difference between those two curves is the interfacial, the G prime due to the interface, and we can use that to follow coarsening, but there's a model for the coarsening rate, but there's not a nice model like we could show to get the drop size out. So we haven't found a way yet to get the characteristic size out, but we can measure the coarsening rate. And we can stop the coarsening with the reactive compatibilization and reduce the pore size. Also, by putting particles at the interface, another area we're doing research in, we can stop the coarsening. But I hope you've seen the way today how we can use rheology to get an idea, to quantitatively really model the molecular weight distribution of a miscible polymer blend, and even extend that to immiscible polymer blends when we have the using the differential scanning calorimetry to get the change in the glass transition temperature, the broadening of it. And then we went to immiscible blends, both droplets, where we can see how we can, if we know the interfacial tension, we can get the drop size. We can see how drops break up in shearing. And finally, we went to co-continuous blends, as we just discussed. So Adil, thank you for giving me a chance to give this webinar, and I'll be glad to answer some questions. Thank you.
Thank you, Chris. Before we continue, I'd like to make everybody aware that there will be a recorded version of this webinar available on the TA website.